Let's go ahead and continue with our example 10.5. So we were in the middle of trying to find out which equation to use, and so we found one, and now we're going to go ahead and solve for the time. So if I go ahead and solve for time here, I get omega minus omega naught over alpha. And so I can plug in my values from the last problem. So omega we found was 220 radians per second. And our initial omega was 0. And our alpha was given as 110 radians. Oh, whoops, we have a different alpha. Right. Sorry. I was like, this is going to give us a circle, but okay. Our new angular acceleration is minus 300 radians per second squared. I also need to note that we are coming to a stop. So let me back up a bit. Since we're coming to a stop, our initial velocity is going to be that 220 radians per second. And since we're coming to a stop, our final velocity will be 0. Okay, that makes more sense now. Okay, so we have 220 divided by 300, and our time to come to a stop for that spinning reel is 0.73 seconds. Okay, all right. So let's go ahead and now compare our angular versus linear variables. Okay, so we have these here. Our position variable in linear notation is x, and rotational it's theta. Okay, in our velocity, for velocity we have dx dt, and it equals to v, but in rotational we have omega, and that's equal to d theta dt. Okay, and for acceleration, our linear component is acceleration a is equal to dv dt. With rotational, it's alpha equal to d omega dt. Okay. Let's quickly talk about centripetal acceleration, since we did talk about tangential acceleration. Let's talk about centripetal acceleration. And that is going to be the acceleration that is pointing inward from the rotational motion. Inward meaning in towards the center of rotation. Okay, so the center of the axis of rotation. There we go. Okay, so if our point here is our center, it's going to be pointing towards that. Okay, and so you can see from this diagram here, our total linear acceleration is the combination of our centripetal acceleration and our tangential acceleration. Okay, so the centripetal acceleration and the tangential acceleration are orthogonal to each other. Okay, so they're perpendicular to each other, and the combination of those two will make up our linear acceleration. Okay, and because these vectors are perpendicular, we can find that magnitude of our total linear acceleration in such a way. Notice how similar this is to other things that we have looked at in the past. Okay, I should describe centripetal acceleration a little more. It is equal to our tangential velocity squared divided by our radius. Okay, and here are a couple of other diagrams looking at our acceleration. So we have our centripetal acceleration pointing inwards, again towards our axis of rotation. Okay, and we have two different velocities. Okay, and as it moves along, or if we have a different situation here, we're applying a tangential acceleration. Okay, then we have another velocity. We have two different velocities, and our centripetal acceleration stays the same. So let's go ahead and look at this in another way. So these are going to be more relationships between rotational and translational motion. So these are comparing our kinematic equations. Okay, so these are the kinematic equations. And then we have our relationships between rotational and what we call translational motion. So translational is what we call like the XYZ type motion, linear motion, okay? That's basically what the translational will be. So we need to know how to have some kind of relationship between rotational and translational, just in case a problem is wanting or giving you things in translational, but you want to know the rotational motion. Okay, so just be wary of that. Know that there are relationships here to combine all of these and relate them. Okay, so let's do an example of this. This is 10.7. It states a centrifuge has a radius of 20 centimeters and accelerates from a maximum rotation rate of 10,000 RPM to rest in 30 seconds under a constant angular acceleration. It is rotating counterclockwise. What is the magnitude of the total acceleration of a point at the tip of the centrifuge at t equals 29 seconds? What is the direction of the total acceleration vector? Okay, so we have our radius. We have some rotation rate that is our maximum. So I'm going to go ahead and say omega naught, because it accelerated from this rotation rate to rest. Okay, so omega naught is going to be equal to 10,000 RPM, or rotations per minute. And we should probably go ahead and convert that. So we have 2 pi radians per rotation, and for 1 minute we have 60 seconds. So let's go ahead and do that now so that we don't forget to do it later. Pi divided by 60. So we have 1,047. I don't know how many units we need to keep. And so this is in radians per second now. Okay. And we're trying to find total acceleration and then the direction of that vector. So we want to find A. Okay. So we have omega naught. We need to find the two components of A. And so that's going to be our centripetal acceleration and our tangential acceleration. So we need to find A sub C and A sub T in order to find our total acceleration. So let's see, what can we do? We have our omega. We have this guy here. Okay. Our omega we can relate to our translational velocity. Our translational velocity here, v sub t. So let's go ahead and do that. So we have v sub t is equal to omega r, omega. Okay. Was the magnitude of the total acceleration at this point, at the tip of the centrifuge. So that radius. Okay. And we also want to know how to calculate our tangential acceleration and our centripetal acceleration. So centripetal acceleration, A sub c, is equal to v sub t squared over r, I think it says. Yes. And so then we want a sub t. Let's go back quite a ways. We talked about it back here. Yes. Tangential acceleration is equal to r alpha. I guess that's all we're going to get. Whoops. R alpha. Okay. So we need to find some alpha, it seems like. And then from there we can solve quite a bit. So let's see. We'll need to use one of these equations. We have that we need to find alpha. So we want alpha. We do have a time, and we have an omega naught. We don't have an omega though, because our final omega is not known, since we are asking about this magnitude of the acceleration at t equals 29 seconds. Okay. We do know that it comes to rest after 30 seconds. Okay, so I could say omega at 30 seconds is equal to 0 meters per, I'm sorry, radians per second. Okay, sorry, this is a pretty complicated problem. If it seems like I'm all over the place, it's because there's a lot of little components that we need to figure out. Okay, so we probably could use that in order to find our acceleration. So our omega we do have for 30 seconds. So we could use this equation here to find our acceleration, because our acceleration is constant. It stated that in the problem. So we have a constant angular acceleration. So let's go ahead and do that. So we have omega is equal to omega naught plus alpha t. And we'll solve for alpha. So we have omega minus omega naught over t. Sorry if my voice starts to go again. Omega, our final, is 0 meters, I'm sorry, radians, I don't know why I keep doing that, per second, minus our initial, which we found was 1,000. I'm going to go ahead and round this to 50 radians per second. 50. Just because I think we'll only need 3 sig figs. So there we go. And our time is going to be 30 seconds because that's how long it takes to stop. All right, so we have 1050 over 30. And we get negative 35 radians per second squared. Okay, so that is our acceleration of the centrifuge. Okay. Okay, so that was our first step. Okay, we need to also take into account our direction of the motion. So it's rotating counterclockwise. So we need to figure out what direction our acceleration is. Both the centripetal and our tangential and our overall acceleration. And to do that, we are going to need our direction of the angular acceleration. Okay, so again, like I said, this problem seems a little simple, but it is not. There is a lot of components, and I think it's good for us to do it together. That way you'll be ready for anything that's on the homework. Okay, so we'll continue this problem in the next video.